Okay, I'd like to take a look at the simple power rule of derivatives. All right. The simple power rule of derivatives basically says that if you have a function f that's defined by a power of the independent variable, it doesn't have to be x, but any power of the independent variable. The independent variable in this case is x. Here's x to the nth power. That's the expression we're looking at. Where n is a real number, so n is a real number, then the derivative of f is denoted f prime and is given by this expression. So f prime, which is called the derivative of f, is equal to n, which is the original power, the original exponent, times x, the independent variable, raised to the power of n minus 1, one less than the original exponent. All right. Now this works on different kinds of functions. Let's look at a few cases that this would work. Case 1 is where n is a whole number. So n is a number like 0, 1, 2, 3, 4, 5, 6, and so forth. So in those cases, when you're calculating the derivative, it still comes into play um, what we are looking at here. Uh, this is the rule for finding the derivative. Let's take that along with us. So in this case, if you want to find the derivative, well, this is x to the nth power. It says that the derivative f prime of x is equal to n, the original exponent 5, times x, the independent variable, raised to the power of n minus 1. 5 minus 1, 5 minus 1 is 4. So this would be the derivative. Now, we all know that we could find the derivative by using one of the limit definitions, but this is a shortcut to that limit definition of a derivative. All right. So if n is a whole number, basically you have a polynomial here, a monomial of degree 5. So if you have an nth degree monomial, then the simple power rule will allow you to take the derivative. Here's something else. This is not a polynomial. Case 2 is where n is a negative integer. This is a rational function, all right? So even though the power of x is written in the denominator here, we can still write it as a power of x if we make that power of x negative 5. 1 over x to the fifth is the same as x to the negative 5 power. Those are equivalent statements. And then once again, we have our derivative rule. Here's our derivative rule. In this case, instead of positive 5, n is the real number negative 5. That's actually a negative integer, So we calculate the derivative this way, f prime of x. N is negative 5, so that's going to be negative 5 times x, the independent variable, raised to the power of negative 5 minus 1. Negative 5 minus 1 is actually negative 6. In the same way that we had to rewrite the original problem as a power of x, when we get the answer, the derivative as a power of x, we have to rewrite it in its form as a rational function. So we switch this back over, negative 5 becomes the only factor in the numerator left, and x to the 6 goes back to the denominator. So the derivative of 1 over x to the fifth is negative 5x over x to the sixth. So we have those two cases, the case of a monomial, a positive whole number, the case of a negative integer, a negative integer. The third case is the case of a rational number. When I say rational number, I mean a non-integer rational number. Like this case, you forget sometimes that radicals can be written as powers of the radicand. In this case, the radicand is x. It already has its own power, but I can raise x squared to the power of 1/5, and it would represent this exact radicand. So x squared, I can raise that radicand to the power of 1/5, and it means the same thing. And when I raise something that has a power to another power, I multiply the exponents together. So this turns out to be just x to the 2/5 power. So this is what we have. We have f of x is equal to x to the 2/5 power. And the only stipulation was that n had to be a real number. 2/5 is definitely a real number. It's a rational number, which is a subset of the real number system. So we're going to take the derivative here using the exact same rule. Same rule applies to all of these cases. So this says that the derivative f prime of x is equal to n. In this case, n is the number 2/5. 2/5 times x to the n minus 1. Well, 2/5 minus 1 is 2/5 minus 5/5. 1 is 5 over 5, right? And 2/5 minus 5/5 is negative 3/5. So the exponent here is negative 3/5. So once again, I have n, which is 2/5 n, times x, the independent variable, raised to the power of n 2/5 minus 1. 2/5 minus 1 gives me negative 3/5. All right, once again, I have to simplify this a little bit. The first thing is I have to get rid of the negative exponent. That means I take this factor to the denominator, x to the 3/5, positive 3/5 now. Also, I can't leave the rational number for the exponent. I want to rewrite it in terms of radicals. So this is going to be 2 over 5. And because the denominator is 5, that's still my index for my radical. 5 becomes the index for the radical. And the numerator is the power of x that I have as the radicand. So x to the third power. So the answer here, that the derivative f prime of x is equal to 2 over 5 fifth roots of x cubed. 2 over 5 fifth roots of x cubed. All right, another case where this works is the case where n is irrational. This is kind of, the typesetting isn't great here. This is x raised to the power of square root of 2. So the power here is an irrational number. We can still use the power rule here. We can still use the power rule for this particular function to find the derivative. Let's see. Here's the power rule again. The power rule says as long as n is a real number, all I have to do to find the derivative, f prime of x, is take n, make it the coefficient, so multiply out front by n is the square root of 2. And then I raise x to the power of n minus 1, which is the square root of 2 minus 1. Those are not like radicals. I can't subtract them. So I leave this as the final answer for the expression. So there you see it. The general power, or sorry, the simple power rule. The simple power rule can be used on a few different cases. It's not just things that look like this, where you have a monomial, but you can also use it in the case of certain rational functions, in the case of radical functions, and also in the case where you have independent variable raised to an irrational number. You'll see less of case 4 as we go through. All right.